In this video, I'll be showing two proofs that the Earth is flat. In the first half, I'll show how there is no curvature on the horizon, even though there are those that claim that lower portions of buildings being blocked from view by the horizon is the result of curvature. The second part of the video is dedicated to showing that the horizon is very thin. It has no depth to it, and that is evidence that the horizon is the product of perspective and cannot be the product of curvature. Okay, let's go. Hi, I just want to talk about videos like this on YouTube where someone zooms in over a patch of water and they actually zoom in on the horizon, which is really cool. But you can see objects past the horizon, whether it be buildings or ships or something, and the lower portions are blocked from view. Well, the average person looks at that and says, wow, that's curvature of the Earth. And, that's understandable. That's what we've all been taught. What I want to show is that it can't be curvature because there's no curvature on the horizontal axis. And what I want to show is that this is perfectly consistent with perspective. This is exactly what we would see. So here we go. Okay, a little something of how perspective works. See the red and the yellow line. The yellow line is your eye height. The red is the ground plane. And the ground angles up. It visually angles up to your eye level. It's on a trajectory. So the way perspective works on a flat plane is that where that intersects, the ground plane and your eye plane intersect, is where the horizon will form. So you won't see any more ground past this point. Once it intersects with your eye, right, it intersects with the center of your eye, that's it. You can't see any more ground past that point. You could see objects beyond it, but they're going to start to get blocked by that point where the ground stopped. And they're going to get blocked from the bottom up. Okay, and for those who don't believe that the horizon goes to your eye level, that all the parallel lines and planes angle to your eye level, just take a look at that wall down the left-hand side there, right? The bottom angles up and the top angles down, and where it converges is right in the center of your eye. That's where your horizon forms. The ground angles up to your eye level, and then you can't see any more ground past that point. You know what I mean? The ground comes up like a big wall. It's a big ramp. And when it gets to your eye level, you can't see any further. You cannot see any more ground, or in this case, any more water. You can see beyond it, but the bottom portions of things are blocked from view. So that's the reality of our vision. Wow, look how that water ramps up to your eye level, and it forms a wall. Incredible, zooming in on that horizon. Notice the buildings behind it, the lower portion is blocked. That's due to perspective. To explain this illustration briefly, when they say they see curvature when they're looking at the buildings, and they're saying because the lower parts disappear, they're calling that curvature. That would be on the z-axis. That's from our eyes to the horizon and beyond. On the x-axis, these are the two that we're concerned with, the z and the x. The x-axis is the horizon, or our horizontal axis. And the x-axis is the one that we don't see any curvature on. They claim to see it on the z, but they say, oh, you can't see it on the x. Well, you should and you must see it on the x, and yet we do not. Okay, here we are looking over the bay. I have it mocked up here so you can, I have the x, y, and z axis, and I got a line across the horizon. And you'll notice I have a guy over there on the right-hand side of the screen, and he's looking across to the left. So the point of this is that here we are looking across this patch of water, and the guy on the beach here says he sees curvature because the building's way off in the horizon. Once you zoom in, the lower parts disappear, so he's claiming curvature on the z-axis. Yet, we take this guy over here to the right, and let's say he's doing the same exact thing. He's looking across the same patch of water, and he sees buildings off in the distance, and the lower portions disappear, and he's claiming curvature. Now, his z-axis is our x-axis. So we should see his curvature. See what I'm saying? So what I'm going to do here in a second is I'm going to zoom in on this whole, the zoomed out shot of the horizon, and we're going to scan it from right to left, and we're going to show that there's no curvature on the x-axis. Okay, here we go. Look for any separation between the horizon and the straight yellow line. especially at the beginning of the picture and at the end, or the right side of the picture, that's where they say you'll see curvature. So we look and we have, I put a little gap between the line and the horizon, and there we go, looks perfect. Okay, and we're going to maintain that gap all the way across. You know, I can't believe they try to get away with this, you know. They say you can't see curvature, but then they see the building's lower portions disappearing and they yell curvature. But here we are. Here's the horizon. Nice long patch of horizon, and let's look at the end. Perfect. Not an ounce of curvature. Okay, I just want to say a word about zooming in with a telescope. There are people that think that I've spoken to that if you use a telescope, your horizon will be further. The stronger the telescope, the further the horizon will move away from you. But I don't believe that's the case, because I believe the horizon is a product of the height of your eyes. The horizon is determined and formed by the ground visually angling up to your eye level. As you see in the beginning of the video here, where he's zooming in across the water, you can see a horizon form, and then as he keeps zooming in, the horizon doesn't get further away, the horizon gets closer, and it gets bigger. He's zooming in on the horizon. That horizon is formed whether you're looking at it with a naked eye or a telescope. All of the telescope allows you to do is to see it larger. See this picture on the top here? If the lines were parallel and perspective wasn't a reality, then yeah, the stronger the telescope, you could just see parallel to the ground. But the fact is, perspective causes the ground to visually angle up. And where that intersects is your horizon, and it's regardless of whether or not you're using a telescope. Concerning the convergence lines that go to your horizon and your eye level, I just want to show you a few slides from my Perspective Horizon Flat Earth video. Which, by the way, is also down. I haven't put it back up yet. Here's a great example of perspective. Notice that the parallel lines do not angle or converge towards the ground, nor do they angle towards the ceiling, nor to the left or right. They angle to the eye level of the observer. This image is a product of our eyes. These are horizontal parallel lines, yet we see them not as parallel, but on an angle towards a point in the distance. Now, of course, we know that they are parallel, but they visually are not. Here you can see parallel lines made up of bricks on the walls. The wall on the left, though, is headed out towards the horizon, and all the lines angle toward the eye level of the observer. The bottom ones angle up and the top ones angle down. This is a great illustration of how all the lines angle to your eye position. You can't deny it. All of the lines converge at a center point on the horizon called the vanishing point. Parallel lines above it angle down, the lines below angle up, the sides angle in. The vanishing point is the intersection of the horizontal and vertical axis of our eye position. See, the ground and your eye level are actually parallel, but visually the ground angles up to your eye line. That's why I say you can't look down at the horizon, because the horizon angles up to your eye level. The two, your eye level and the ground plane, are parallel all the way to the horizon, but it's the bottom ground plane that angles up to your eye level. These lines are visually parallel. Our eyes visually intersect the parallel lines at the horizon. Here's a guy sitting in the middle of the ocean. You can see the water angles up and on each side of him to our eye level, actually angles all the way around him. Just like looking down that long hallway, the floor angles up to your eye position, the ceiling angles down, the walls angle in. That's perspective. Here's another one with the guy in the boat. Whether he's in the hallway or out on the ocean, the ground plane angles up to your eye position. And so you can't see any ground past that point once it intersects with your eye height. So items or objects beyond the horizon will be blocked, especially the ground, and then lower portions of objects beyond the horizon will have their bottoms blocked from view. And here's another one. You can see the water ramp up to the eye level, and the building beyond the horizon has its lower portions obscured. It's kind of like putting your thumb out at arm's length and putting it level with your eyes. You can block things much bigger than your thumb. That's due to perspective. And the same happens here. The further away that building is, the more of it gets blocked, starting from the bottom up. Okay, take a look at this picture. And your horizon is a circle, right? So for the average height person, if your eyes are 5 to 6 feet above the surface of the ground, your horizon will form about 3 miles out. So you have about a 3-mile radius to your horizon. Now, the higher up you get, the bigger your circle.
you can see further. So, and think of it like putting a hula hoop, and this is why a lot of people confuse curvature with the circular horizon. They're seeing a circle and they're thinking that's a curve. It's not a curve. Look at this picture with the hula hoop, right? That's all it is. If you put it at eye level and level it, you're going to have that circular hula hoop will become a straight line. Okay, that concludes the first part, dealing with that there's no curvature on the x-axis or the horizontal axis. Now I want to talk about the thin horizon, the fact that the horizon has no depth, and how that is completely consistent with perspective on a flat plane and not consistent with a sloping ball and the horizon being a product of that curvature. So let's go. Okay, here's a really quick zoom. Check out the horizon. It goes really fast. He doesn't stay there very long. Now there's clearly an angle set up between the ground and your eyes. And so this angle of the ground visually angling up is going to intersect with your eyes. And so where it does, it seems like it stops. Like you can see rows and rows of waves here, and the very last row has definition. You can see sky between it. The waves are big, they're clear. Clearly it's a result of perspective. I make a still of that too. I blow it up and you can check it out. Here's another zoom. Okay. Check out the choppiness and the shallowness of the horizon. You can definitely see sky between those waves. Funny how it's as if the horizon just stops. I mean, the ground plane angles up, and when it intersects with your eye position, it stops. Okay, here you can see the shallowness of the horizon. I mean, you can see right between the waves. It's as if it's one layer of waves, right? Okay, just a quick word on this. You can see right there that line across there. There's a mirror image of the sun happening. So this is a phenomenon that occurs quite regularly over the water and over land, as a matter of fact. And that would obscure objects beyond it. Now, I call that a mirror band right there. And so it's reflecting the mirror image of what's above it and flipping it. Right? So you're not actually seeing what's there below the red line and the water. So there could be a boat beyond that, and you're not going to see that boat because it's going to reflect what's ever above it. And in this case, it's reflecting the sun, but next to the sun, it's reflecting sky. Right? So you would think the boat disappeared if it were beyond that mirror band, but it's not. It's still there. Okay, and so here you can see the mirror band is reflecting what's above it. Within the red mirror band is just a mirror image. So the sail has mirrored part of the sail and has flipped it. And so the sail and its image have merged. So it's easy to see why you could look at that and say, wow, where'd the hull go? The hull must have gone below the curvature. Well, it didn't. It's just that the mirror image of the sail is blocking the hull. Look how you can see the sun between those big gaps between the waves. If that horizon were the result of a very gradual curvature, the horizon would be much thicker and much denser. You wouldn't have that kind of definition within the waves. Okay, see the people on the boat? They're just a layer of people, one layer, and see how they look like the horizon? It's as if the horizon is very thin and it just drops off. This is kind of blurred out, but you can see the upward trajectory and then the thin horizon. There's no depth to the horizon. It's as if it stops, and it does. Perspective would dictate that the ground visually angle up to your eye position, and when it does that, it stops. You know, you can't see any more ground behind it. You can see things beyond it, but you can't see the ground. And notice how the waves can block several floors. I mean, 4, 5, 6 stories of those buildings. And the further away the buildings are, the more of them gets blocked. It's like holding your thumb out at arm's length. You can block things much bigger than your thumb. Again, here, notice the thin horizon. It's very choppy. You can see through it. You can see between the waves. And notice on the right-hand side how when the water splashes up in the air, it falls back down on the water and it's obscured by the horizon. Again, that thin horizon is strong evidence that we're on a plane and this is perspective because of the fact that the horizon just drops off. It stops. It ramps up to your eye level and stops. Here's a zoom in on that same shot. Notice the right side of the rocks, the waves splashing behind the horizon. It's really surreal looking. I mean, what a zoom this person used. It's awesome. You see the water splashing down behind the horizon, and it's as if it's a little lower than the horizon itself. Now, none of us know what happens. I don't think any of us know what happens behind or beyond the horizon, whether it flattens out or it goes on a downward trajectory. You know, since the converging lines have already converged, maybe they then go downward. I don't know.
Here I made an illustration using people instead of the water, and I arranged them so that they ramp up to eye level just like the water does when we look out over the water. And you know, many of us have been in a big crowd of people, and when you're looking through just a couple of or a row of people in front of you, it's no big deal. You can look between their shoulders, between their heads, and you can see. But when you get a thick enough crowd and they're all the same height as you, you can't see anything because they block the view. So that's what I've been showing about the thinness or the lack of depth in the horizon that we've been looking at. So I just thought this was an illustration because most of us have been in a crowd and could relate to this. So anyway, in the first one here, you can see that resembles the water as far as it ramps up to our eye level, and the top row of men, you can see sky between their heads, and that's what we've been seeing, as if it stops right there. That's the horizon. That group on the top row is the horizon. And then we have this. This is what we would see if the Earth was a slow, gradual curve. The horizon would be thick. It would have so much depth to it that you wouldn't see between the heads. You wouldn't see the sky between the waves like we've seen in the illustrations I've shown in the video and in the pictures. So anyway, I thought this might help. It's a good way of showing it, I think. So let's recap. There's 2 points that I've made in this video. Point 1, they claim that you can see curvature because the lower parts of the buildings disappearing, or a ship going over the horizon and the lower portions of it disappearing. They claim that's due to curvature, but yet we don't see it on the horizontal line, and I showed you scanning that video, or that picture I mean, and it totally showed no curvature. So that's debunked right there. That's one. And two is this thin horizon, or the fact that there's no depth to it. It seems to stop. Now, if it was if we were on this huge ball, it would be such a gradual curve, right, that you would have a very thick horizon. The waves would be looking through that group of heads when there's a lot of people in front of you, rows and rows and rows, and you can't see a thing because all the heads fill the gap. But that's not what we see, fill the gaps. That's not what we see when we look at the horizon. These pictures, we see sky between the waves, as if there's one layer of waves, and that's it. And so this, the thin horizon, is consistent with perspective on a flat plane, where the ground, there's an angle set up between the ground and our eye height. And when those two angles converge, right, when the ground plane visually angles up and converges with the center of your eye and the height of your eye, that's it. It stops. So that thin horizon is consistent with perspective on a flat Earth.